This example is a quadratic application that has more steps than you're used to. It may look a little different. So I've just kind of drawn out some highlights here. It costs the sweet shop C of x equals 0.01 x squared plus $1,836 to produce X pounds of chocolate creams. The company charges $12 per pound for the chocolates. So we know that our price is $12. Find an equation giving revenue R as a function of X. So X is already declared for us, and so we're good there. The function for cost is given to us. That's a quadratic. And the, let's see, the equation for revenue, the generic is R of X equals P of X. So we have what P is as a number. So we're going to go ahead and put that in. So we would write R of X equals 12X. We want it in terms of X. So I have a graph here off to the right that we'll look at in a minute, sketching the Cnr functions on the same pair of axes. So we're just going to kind of do that by hand really roughly, and then we'll reference the graph I made in Desmos. So if we have the revenue, that one's kind of easy. It's just going to be a straight line coming from 0. It has a slope of 12, but our scale here, because of this y-intercept for C of x, it's pretty big, right? So I might need to do like, I'm gonna probably make these be worth like 1,000 or something like that for each mark here. And I can tell from this other graph that my revenue is pretty steep. So I'm going to try to match that a little bit. But again, we don't need to worry too much. We want to try to make it somewhat straight about accuracy for the graph. We're just trying to get a picture in general to what it looks like. You could even just draw it over here if you didn't want to use a grid. And then I would have the cost. So if I'm saying that, it's like 1,000, 2,000. So that's my y-intercept. It's going to be somewhere around there. I know it curves up, and I know it's pretty skinny because I have a decimal that is less than 1, between 1 and or 0 and 1. So I'm going to try to just sketch this in here like that. Okay. So if I look at my little graph off to the right, I know that I can only make a positive number of items. So that's why I drew it only in the right quadrant. So I really don't need this part here. Oops, maybe don't want to get rid of all those numbers though. I don't want to have negative X values in that. So I'm just going to get rid of those. I also can see where they intersect, and it's just a little bit easier to show on the small graph. So I have these points of intersection. That's when R equals C. R equals C, right here and here. Now, when R is greater than C, we'll kind of highlight that one in, we'll just use yellow highlight, is right in there. So that is R is greater than C. So that is our area where profit will occur. So I just want to point that out and have you start to notice that. So the graph can show us where the points of intersection are, and we just talked about what those mean. That's when revenue does equal the cost, or another way to word that is zero profit. So you can pop the things into Desmos like I did, and you can find your areas of, let's do a different color for that, intersection. Okay, so you would get your X values. We're going to get 180 and 1020. And then in order to find the corresponding y's, you'd have to plug into the function. So how we would do that is using either technology like Desmos, could do that. It'll be accurate because those are the answers that I got using quadratic formula as well. This one is a little bit tedious using the quadratic formula, but you certainly can work that out. So I'm going to do that and show it out. You can pause the video and try it on your own, or you're welcome to go into Desmos and check that out. So I'm going to make this a little smaller. Okay, so I think this is really great review for the final. That's why I'm even bothering to do some of these, because there's multiple skills that we've learned throughout the course and it brings it all back. So here is a quadratic formula that I wrote here. X equals minus b plus or minus square root of b squared minus 4ac, all divided by 2a. So we're just going to go ahead and pop in our, we're actually doing the points of intersection. So the first thing we need to do is set our equations equal to each other and find out when that equals 0. So let me just make some space here. So we would do we want to know when r equals c. So what we're doing here is actually this part. So we would have 12x equals 0.01x squared plus 1836. Then we're just going to set it equal to 0. So 0 equals 0.01x squared minus the 12x plus 1836. So our a is 0.01, our b is negative 12, and our c is 1836. So I'm going to go ahead and put those in. I'm going to pause it and start crunching some numbers. You try that as well and then check back. Okay, so you can see where I popped my values in. So I put my negative b is negative 12, and then I had to put b squared, so I get positive 144. Make sure you use parentheses, so all those old things that maybe we haven't used in a bit. 4 times 0.01 times 1836 comes out to be 73.44. So I subtract those, I get 70.56. Take the square root of that. So I have a square root of 70.56, and that comes out to be 8.4. So then I have 12 minus 8.4 over 0.02, and or, which we just write or, 12 plus 8.4 over 0.02. So I am going to get, let's see, 12 minus 8.4 is 3.6 divided by 0.02. I get the 180. And then if I do the same, I just add 8.4 divide by 0.02. Then I am going to get, I get 1020. And both of those are going to work just fine. So now once I find those x values, which you can see right here on the graph, we would need to plug those in to the function, one function or another, to find out what the corresponding y is. Now I'm going to pick the r value just because, you know, it's easier to work with, it's shorter. So I'm going to do r of 180 and r of 1020. So go ahead and do that. 12 times 180 is just going to give me 2160, 2160, and then the 1020 times by 12 is going to give me 12,240. So that's going to be my actual Y value, the revenue that I take in. But it's also the cost, because those are my break-even points. And then you would write them as a point. So we would have 180, 2,160. That's this point up here. Down here. And then the other point is going to be 10,020, comma, 12,240. Okay. So those are when revenue equals cost. We call those break-even points. Is pretty typical, okay, in that context. You could also say when it's zero profit. The next part here, part D, what production levels result in the company making a profit? So we have kind of figured out from above what the break-even points were by setting the equations equal to each other. Well, profit's kind of similar. We would just subtract them. P of x equals R of x minus C of x, and make sure you use parentheses when you plug in a function. We can also, it'll actually come out to be similar to what we calculated before. So we have P of x equals 12x minus parentheses 0.01x squared plus 1836. Then I distribute that negative. So I get 12x minus 0.01x squared minus 1836. So that is going to be my profit function. If I just rearrange that a little, it'll look a little bit more like a quadratic with the middle term there. So I'm just going to write that here. P of x equals minus 0.01x squared plus 12x minus 1836. Just so it kind of looks like how the format, descending order. So we know that in this case, it's going to open down like that. And then we'll have a y-intercept will be at 1836. So it'll be maybe something like that. So we have the function. Now we need to know what productions levels will result in making the profit. So really anything between, we kind of look at our graph again, anything between these break-even points, that's going to be our levels that make a profit. So the answer for that would be between 180 or 1,020 items. Because what's going to happen here, if we put 0 in for profit, we get our break-even points. And anything in between those is going to be actually the profit. So our answer would actually be the same right here. That it would be, I'll write it right here, between 180 and 1,020 items, or is it number of pounds of chocolate. Chocolate creams. Okay, so that's, we have to be somewhere in that. Well, what value is going to actually give the maximum profit. A lot of times it's worded as maximizing, okay? So we want to know where that vertex is, our line of symmetry. Which X, the number of pounds, is going to give us the highest profit. So we would want to use our minus B over 2A and figure that out. So we're going to use our minus, our B is over here, remember 12. So it would be minus 12 divided by 2 times negative 0.01. That'll just be 12 divided by 0.02. They're both positive, so I get 600 pounds of chocolate. And that'll give our maximum profit. Well, if you want to know exactly what that profit is going to be, then you need to take that 600 and plug it in for your into your P of X. So we're going to find now P of 600, and that will end up being negative 0.01 times 600 squared plus 12 times 600 minus 1836. So go ahead and crunch those numbers, and we'll get minus 3600 plus 7200 minus 1836, and it comes out to be $1,764 is the max profit. So a lot of steps with that one. So just, try your best with these, is just really preparing you. There might be a couple problems for you to try. So the next problem is one that maybe you could try on your own. It's a little similar. This annual increase I in the deer population in a national park depends on the size X of the population that year, according to I of X equals 1.2X minus 0.0002 X squared. So it's a little bit similar setup. It's not a cost and profit problem, but it's a, kind of more sciencey. So if you're in business, college algebra, the intermediate algebra, math 99, you may not want to do this one, but it still provides you with the practice on the similar skill of finding your zeros and graphing, sketching, and stuff like that. And we also are going to review average rate of change. So see if you can try to set some pieces up to that, and then I'll quickly walk you through it. Okay, so we have any horizontal intercepts of the graph that we want to find and explain their meaning in everyday language. So this one actually factors out pretty nicely. So we're just going to set I of X equal to 0, because that would give us our x-intercepts, and we're going to factor out an x. And then we have 1.2 minus 0.002x left in parentheses. And so our zeros would be x equals 0. Or if we set 1.2 minus 0.002 equal to, or 2x equal to 0, then we will get 6,000. I'll clean that up a little there. Okay, I'm missing a 0 now. Okay, so should have 0.0002x. And if we set that equal to 0, we'll get 6,000. To find the corresponding y values, to write these as points, you would just put them right back into the function. So if I put 0 in up here either spot. If I put 0 in, I'm going to get 0. And we know that anyway because it is an x-intercept. And if I put 6,000 in, I'm also going to get 0. So I can just kind of double check my work that way. Okay. So what this means is when there are no deer in the park, the population does not increase. When there are 6,000 deer in the park, then the population also does not increase, because that's what I of x means. It's an increase. It's not like saying that it's actually a number of deer. It's how much it increases. Okay, so it's not how many actual deer, it's how much the increase was. Okay, so I'll write that out for you. So I think the 0 deer not increasing in population resulting in an increase is obvious. I mean, if you have no deer to start with, they're not just gonna, spontaneously appear unless someone adds them in. But if you have 6,000, you think like, why wouldn't it just keep going? Then more and more deer would be born and stuff. Well, what happens is there starts to not be enough food and things like that, so they'll start dying off. So there's going to be a decrease actually. So part B is find the vertex of the graph and explain its meaning in everyday language. So the vertex, we would use minus b over 2a. So go ahead and plug that in and calculate that out. So just take a minute to do that. You can pop that in. B is 1.2. A is negative 0.0002. Okay, so crunch those numbers. You should get 3,000. So that's when we're going to have the maximum increase, when we have 3,000 deer. To know exactly what that is, so that's just giving us the x value. If we want to know I of x, we would need to put the 3,000 in for x. So we're going to find I of 3,000, which will be 1.2 times 3,000 minus 0.0002, 3,000 squared. So go ahead and crunch those numbers. And we end up getting 1,800. So this is going to be my max value, the y value. So the vertex is going to be 3,000 and 1,800, an increase of 1,800 deer when we have 3,000 deer. Okay. The next question, find the average rate of change of I from x equals 0 to x equals 3,000. So that's just that increasing piece from 0 up to the vertex. So when the deer population is at 3,000 deer, we can expect that we'll have a max of 1,800 deer, and then it like maybe drops off after that. So we're trying to look at the average rate of change on this, like kind of right in here, okay? So we're going to use our Quadratic formula, change in y over change in x. Be careful not to switch those up. So we have 1,800 minus 0 over 3,000 minus 0, and that will reduce down to 3/5 or 0.6. You might want to think of it as, we could think of it as the x values is the number of deer. So we might think of it as like if you were to add 5 deer to the population, then the annual increase would become 3 deer. Or you could word it the other way around. So I just wrote it as there will be an annual increase of deer for every 5 deer added to the population. Oops, I forgot to put of 3 deer for every 5. So now we're going to sketch y equals I of x, which I kind of did right there, but I can make a bigger one right below, give him more room. So I have, like, say this is my 3,000, this is my 6,000, this is my x, which is the number of deer, and then this is I of x, which is my increase in deer. Okay, so for instance, if I had 5 deer and I increased by 3, then I'm going to have 8, right? So here's a scale. So I would have my 3,000, 1,800 would be right there is my max curve. My intercepts are at 0 and 6,000. So in my domain, I wouldn't have any negative, but I'm just going to draw it kind of crossing through. Because obviously, you know, we wouldn't get negative deer. So we have, this is the increase function. One thing I want you to just get in the habit of labeling your vertex, 3,000, 1,800. Okay. So that means there's really, at this point, the next year, if you increase by 1,800, you would have 4,800. So part E is draw the lines y equals x and y equals negative x on your graph. What is the significance of the intersections between I and these lines? So if you had your increase equaling your number of deer, for instance, you would have a line that would kind of go through right like this. That's the line y equals x. Goes right through the origin like that. And there's also the negative one. This one, I'm actually not going to get too much into that. We get more into that in like pre-calc. So I think we'll just skip that. I just wanted you to see how these lines go. For now. And then let's look at find a reasonable domain for the function. So if we have our intercepts at 0, 0, and 0, 6,000, what would it make sense? Oh, there should be another 0 there. For our x values to be, well, somewhere in between there. So I would say maybe not equal to 0. Maybe I'm going to start with like 2 deer and then go up to the 6,000. And then it is going to start going down. So that's it for that one. Okay, so I actually didn't make separate videos for all of these, but I think we're going along pretty quick. So Number 3, a farmer decides to enclose a rectangular garden using the side of a barn as one side of the rectangle. What is the maximum area that the farmer can enclose with 60 feet of fence? What should the dimensions of the garden be to give this area? So let's kind of think of our little barn here. It's not a very good barn. Let's try to make a better barn. It's like a barn like this. Okay. And so he's having, part of this is enclosed by the barn, and then the fence is going to be off it. So I guess this part of the barn probably. And then the fence will come around like that. And we're going to have like a garden in there. Right? Probably not flowers, but veggies or something. And so we would have, I would have a width on the right. So I have 2 widths and 1 length, because remember the other length is actually the side of the barn. And I know that my perimeter, the fencing I have is 60 feet. So this right here, the width plus length plus width has to equal 60 feet. 60 equals 2W plus L. Now I can solve for L in terms of W. I think that's the easiest route for me to go. And how I would do that is just subtract 2W from both sides. So I would have 60 minus 2W equals L. And we've done that before with literal equations. The other thing I need to take into consideration is what I'm looking to do is find the maximum area. So I need to relate the area formula in here somewhere. So area is equal to length times width, that's standard formula. And we're going to take and plug our 60 minus 2W in for length. So area equals 60 minus 2W. You've probably done these kind of things before when we were doing quadratic functions and stuff. We just didn't do the like maximum. So that's the new piece. So now we're going to distribute that W. So we will have A of W equals 60W minus 2W squared. And if we think about that, it's going to be a curve like this because our A is negative. So what would our maximum area be? We would need to figure out minus B over 2A. So we're going to get our line of symmetry. And if we plug those numbers in, we'll get minus 60 over 2 times negative 2. So we're going to get 15, and that's in feet. So that's going to give the maximum area is when X is 15. So if X is 15, what is length at that X value that maximizes? So we would just simply take that and put it back in, not X, but I guess we're calling it W. We're going to plug that in for W because we know L equals 60 minus 2W. So if we want L of 15, when the width is specifically 15, our length is going to be 60 minus 30, which will be 30 feet. So the dimensions that we need will be, so that's part, what should the dimensions be? Part 2. So the dimensions we need to maximize is going to be 15 feet by 30 feet. But the area, we figured out a piece of it. We know that the width is 15. And then we also figured out that the length is 30. So the max area, we can just plug back in here, should be 15 times 30. So 450 feet square. And that's it for that one. So have a great day.